Good evening, sir.
Good evening. Hello everyone. So let's begin. I think probably I waited for 10-12 minutes so that if anybody would like to join, so that they can join and they don't miss the lecture. So today we entered in the week ninth of our course, and I hope that you guys are doing good with your subject. And if you are facing any kind of a problem, please try to reach me, or you can also ask me during the class, as well as you can email me if you will have any kind of a doubt regarding the course. So simultaneously, if you could not attend any of the lecture by any chance, you can watch the videos in the YouTube. uh, and yeah, so anyways, let's begin the course. So, welcome everyone, and my name is Saurabh Soni, and welcome to the week ninth of the doubt and problem solving sessions in the course of carbon materials and manufacturing. So, this week we'll be covering mainly the concepts which is related to the which is covered in the lecture of week 9. After covering the concepts of this week, we'll try to solve some problems, could be numerical and some conceptual questions. So firstly, I will be giving you some concepts which have been covered during the class, and if you will also, I hope that you have seen the lectures, and probably if you will have any kind of a doubt, then please try to discuss, and yeah, I'll try to solve that problem. And so let's begin with our concept. So during the last class, we have covered till this carbon based composites, and how what are, and some machining parts, how these machining parts take place in the carbon reinforced polymers, carbon fiber reinforced polymer, as well as we have seen some composites and some applications, and how it manufactures, what are the applications, and how can we manufacture it in the industrial grade. So today what we'll be doing is we'll be seeing some more new concepts, which is very interesting. And let me take my pen. So I hope I'm audible, and if not, then please let me know. Yeah. So today we'll be mainly seeing and regarding us concepts carbon composites again, but with non-polymer matrix. Okay. So earlier in the class till now, what we have seen is the carbon fiber reinforced polymer. Okay. So here what we will be seeing, what we were seeing is the two things were there, matrix and the reinforcement. So in the matrix part, we were taking the carbon material, and in the reinforced part, we were taking some polymer or the plastic material. Okay, so these were our composite mainly till the last lecture. But what we will be seeing today is that the carbon composite, okay, so here two parts will be there again, the matrix because it is a composite, and the second part is your reinforcement again, but the matrix will be your carbon again, but the reinforcement part will not be your polymer, it will be your non-polymer. It could be anything, it could be a ceramic, it could be a metal, and it could be a carbon, it could be a concrete. So here you can see this is your carbon composite. So first thing what we can reinforce is the carbon. Okay, this is the polymer which we have seen till the last lectures, which is known as the carbon fiber reinforced polymer. So here we are not mixing the polymers. There are a range of polymers where we are mixing a non-polymer matrix. Here it is a metal. Metal we are mixing as a reinforcement. The next thing is your ceramic material, and the ceramic is also one of the good in order to enhance the property. And the another one is your concrete. Okay, so what we'll be mainly seeing here, the first thing is your carbon based composite. Okay, so first is your matrix material. So matrix material, it could be a polymer, it could be a metal, ceramic, etc. Second thing is your shape, structure of the additive. Okay, so how it can be, affect the shape and the structure. It could be a fiber shape, it could be a tube like carbon nanotube, it could be in a particle shape and all. I mean, it could be any form. The third one is your, okay, so this one is your first, this is your second, this is your third. Size of the additives. You can add any kind of additive in the nano, in the micro, in the millimeter scale. Okay. So, can anybody give me the example of this particle? Like, where have you seen this nano, micro, or milli? I mean, additives kind of a thing, or what we usually call that.
Can you repeat the question, please?
I'm saying, like, suppose if we are adding any kind of additives like nano, micro, or milli. So, what basically you will call that material? Or let's say if you are adding some nano, then what it could be, or how will you define it?
We are talking about.
Yes. Okay, let's say a nano. Okay, so for an example, if you will having a let's say a composites, okay, where you are adding a particle and it has a size of 10 is to power minus 9. That's mean it is in the nano range. Okay, nanometer. So nanomaterial is what? I mean, there you will have a particle which is very, very smaller. Okay, then you can have a micro where your particles range should be in the range of micrometer, and then the millimeter. Okay, so it depends. I mean, the thing is, a lot of things you can vary by adding this kind of a particles. Let's say a nanomaterial. Why you should add the nanomaterial? So, can anybody give tell me that is there? I mean, any specific things that you can alter or you can change by adding this kind of additives, or if you have seen in any material using additives, and for what reason, for what applications.
You can change the mechanical strength.
Okay, so the okay, so I'll be note it down here. Okay, so let's say you have you can change the mechanical property. What else? Yes, you are
Thermal
right.
conductivity of the composite material will also change.
So you, let's say you can change the thermal property of the material. What else? Can you change the electrical property? Right?
Yes.
Okay. So, and there could be many more. It's not just you can change the physical property also. Okay, you can change the physical, you can change the some density, you can change the what else? There are a lot of things you can change by using this. But mainly as a material scientist, we are mainly interested in electrical. mechanical. So let's say you can change the resistance or the capacitance or the inductance, depends on the material what you have. You can change the property, okay, and also it depends on the what the material you are adding, whether it is a nano material, whether it is a in the millimeter or the micro material. It depends on the many properties of the additives that you are adding. Okay. In the mechanical property, you can change the strength, which is UTS, ultimate tensile strength. You can change the Young modulus. Okay, yield strength you can change. You can change the Young modulus. In the thermal property, you can change the your thermal conductivity. You can change the specific heat. You can change the enthalpy, and many more property could be there. Okay, so the main thing is that suppose if you have a material A which cannot meet the property what you want, but if you can add some material or additives to B, it will give you the property of your desiredness. Okay, so in this case the material B is enhancing the property of material A such that you can use in the required application. Okay, so where have you seen this kind of a composites application? Mainly the most common, or you can say the most versatile, or let's say you can say where you can see it's in the aircrafts. In the aircraft, how much sensitive it is. You should have a very good strength. You can have a very good thermal property that it cannot and some corrosion related property, whatever it could be. Okay, so here the material you are using, that should be a very well established. So in this kind of application, your composite play an important role whenever you will have this kind of material where you cannot compromise with the quality of your material. You need to have certain kind of a specific required property that can meet the desiredness of the application that you want. Similarly, even though if you are using some home kind of a material which you are regularly using in your home, but you still you want, suppose if you are using a, let's say, a plate in which you are eating. Okay, so usually we use like a steel. We can't use, have you seen anybody using in a kind of a iron plate or something like that? No. Why? Because we want certain specific. Suppose if we have something which is a salty or it's not in a nature. Okay, it can affect the properties of your plate or the utensils where you are eating. So steel is in that sense a material which can like a non-corrosive due to its composition. So it is meeting the required property that you want for that particular applications, right? Similarly, let's say in the water application, in the marine. Okay, so in the marine, if suppose if you have seen any kind of a yacht, you can say, or cruise or ship. Okay, so that should have some kind of a property because it has to expose continuously during the long period of time to the water. And let's suppose if it will have some kind of a property that can start corroding when it came in contact with the water, then what will be having will be a big trouble. Like, so it should have what kind of property? It should have a good strength. It should have a non-corrosive property that when it will come to the contact with the water, it should not corrode, right? It should have some temperature resistance because there will be a lot of motors and heaters, inside the machine. So application, so the most important thing wherever you will go is your application. Okay, how these all materials have been developed till now is all depends on the applications. You require this property, you need such kind of material. Okay, let's say it is application. Okay, then you will find the what is the material. You can't find material, then what you will do, you will do research. And in this research you will find, okay, let's say if we will be using, there is no material which can give all this property, let's make this kind of a composite, or you can say alloy, which can give me a certain or certain specific property. Okay, so this is how the application is the main thing that will lead you to, you know, motivate you to find some new materials and the materials property and the usability of that material. Okay, so that's why the carbon composite is the kind of a material which will give you a, a so good property that you can see wherever you will go. Nowadays a carbon composite material is the most advanced and versatile material that has been using in lots of applications due to its specific property, right? Then the fourth one is your functions. Few functions induced in carbon materials that you will see, there are a lot of functions. Most common reinforcement is carbon fiber, but carbon nanotubes, graphene flakes, carbon particles, and even 3D carbon structure have been used as additives. Okay, so here it is saying, let's say if you will have a carbon matrix, you can use here, you can make some graphene flakes, you can add some carbon nanotubes, you can add the carbon particles, or you can add some 3D structure. I mean, there are a lot of you can say the allotropes of the carbons that you can add in your carbon, so that can make a carbon composite, or you can say let's say this kind of a carbon carbon composite, where you will be adding a carbon, the different form of a carbon material in order to enhance the property, because each carbon gives their different property. Okay, the second thing is in the carbon carbon composites are primarily carbon fiber reinforced carbon. So till now we will be using carbon fiber reinforced polymer or plastic. Now here we were using a polymer, but now here we are using a carbon fiber reinforced carbon itself, CFRC. But in principle, any carbon additive in carbon matrix is called carbon carbon composites. So it's the same thing which I was saying, carbon carbon composite, where your matrix is itself a carbon material and your reinforced part is also a carbon material. Okay, so when you want certain kind of a property, but yeah, the things to be noted is that this can be a different form. Okay, suppose let's say if your material A is your carbon, so your material B should be like a graphene, it could be a carbon nanotube, it can be a different form of a carbon in order to enhance the property or the specific desiredness that you want. Is it clear?
Yes, sir.
Okay, so have you seen anywhere where where you have seen the carbon carbon composites?
I haven't seen, but we generally prepare electrode material like with carbon as a base, and uh, we can use carbon like graphene oxide or something as composite. No?
Okay, for what?
Electrode material for energy storage.
Okay, and anywhere else? Anyone else? who is present here, have you seen any kind of a carbon-carbon composite or any application where have you seen this?
Reusable materials weapons.
Yes, somebody is saying. Yes, please say. Hello. Somebody said something. I could not hear properly. Okay, fine. We'll be seeing. Don't worry. So, yeah. So in carbon-carbon composites, okay, it is also known as your uh, carbon fiber reinforced composite. The second name you can pronounce this carbon-carbon composite is carbon fiber reinforced composite. So where can you use this? It should have certain property or applications where your matrix will be carbon and you are adding reinforcement in order to get some property. So what it could be? So this CFRC will have a good mechanical strength. Okay. So in the application where you want a very good mechanical property, there you can use this CFRC. But the challenge is here. Let's say suppose if you're in the applications where that part is getting heated, okay, so it cannot be exposed to the high temperature, right? So you cannot expose this to the high temperature. It cannot sustain the property. It will starts to deteriorate. Now the advanced this carbon composites include high performance carbon fiber and carbon nanotube based composites. So it is saying that you will have carbon and the carbon fiber, carbon and the carbon nanotube composite. Okay. So this is saying this is the plot. Okay. So this plots will mainly give you the uh, property where what kind of a composites you will be using as per the strength required. Let's say you are this is a temperature required and the strength required. Okay, so let's say if you will require a very high tensile strength around this 700 to 800 megapascal in this range. Okay, you are not I mean in this region you don't need a very high temperature. Then what will be the good option? Carbon fiber reinforced polymer, because polymer cannot sustain a high temperature, although it will give you a best mechanical strength or the best mechanical property, so that you can use it for the good mechanical property kind of applications where you will require a good strength. Okay, so this is your carbon fiber. GMC is what? Glass matrix composites. So here you will use glass matrix. Okay, so in the glass matrix it will have a certain a good mechanical strength, and also you can expose this to a little higher temperature. Similarly, a glass ceramic matrix composite, so here you will have a glass and ceramics. So here you can see there is a reduction, a little bit reduction in the mechanical strength, but it's not very significant, but it can sustain a better thermal, or you can say a temperature, so that you can use it for the where you will require a good mechanical property as well as the thermal property. The The fourth one is your CMC, ceramic matrix composite. So here you will be using a ceramic matrix. So in the ceramic matrix, because ceramics, you can expose this to the higher temperature also, and it will also have a good mechanical strength. MMC is your metal matrix composite. Okay, so here you can see aluminum metal matrix composite, titanium metal matrix composite, nickel metal matrix composite. Okay, so in the aluminum, it will have a good mechanical strength, but the thing is you can't go very high temperature. Okay, somewhere you have to get a balance between the strength and the temperature. In titanium, it can go certain higher temperature, but strength is also good. In the nickel, the strength is not good, but you can expose till the higher temperature. After that, it will come a carbon-carbon composite. The carbon-carbon composite is saying that the strength is fairly good, as you can see, and also it can go to the higher temperature. That's why this carbon-carbon composite is very well used nowadays. Silicon carbide, here you can see. So silicon carbide is also strength is very low, but it can expose to the higher temperature. I mean, it can sustain higher temperature. This is composites made of silicon, aluminum, oxygen, nitrogen. So it is something that has a mechanical property not very good, but the temperature resistance property is fairly good. Okay, so this diagram will help you to find out the composite as per your requirement, that what strength you want and till what temperature you have to expose this material. Okay, and on the basis of this true property, you can choose the material from this diagram, that which material can go suitable with your application. Now, the strength of some engineering material, it is saying the temperature. Here the carbon-carbon composite exhibit high strength at high temperature, okay, in non-oxidizing atmosphere, it is saying. So let's say if you are going to the more than the 3000 degree 3000 degree centigrade, but if you will use oxidizing, it can oxidize and the strength can reduce. But if you are using some inert atmosphere, then probably you can have a good strength. Okay, is it clear?
Yes, sir.
So have you used any time, anybody have been using or have used any kind of a composite material, or not used? Maybe if you have seen somewhere in any good applications, you can say probably.
You're asking specifically carbon-carbon?
No. Any kind of a ceramic, metal matrix, ceramic matrix, polymer matrix, carbon.
Yes. I have seen composite, like we prepare different composite materials. So,
For what? What material?
um, nanomaterial composites, basically.
Nanometric. Okay, nano. If somebody is saying nano, does
Yes.
that mean is there is something which is in the nanoscale, but you can't say a nanomaterial composite, because composites, the material itself, you have to define certain kind of a material, whether it is a, let's say in a broad level of metal, some metal should be there. Carbon, there should be some carbon. It could be a nano in the nano range size. It could be a ceramic, which can be a nano range size. So any kind of mud that you have to some specify the material. I mean, you have to tell the material.
I mean, like there can be a composition of to nanomaterials, right?
Yeah, definitely. But there should be, if you are saying composite, then there should be some matrix, there should be some reinforced. Although it could be possible that both the matrix and the reinforcement are in the nano range, but
Huh.
it should be some material. I mean, you can say, let's say a polymer, metal polymer, nano composite, that is defining it is a nano composite where basically at least one material is in the nano range.
Yeah, so polyaniline and graphene oxide.
Okay. So for what you have seen?
As actually I work with energy storage, so most materials which I see are related to that. So that is why again
Okay.
the same use for batteries, supercapacitors, those
Okay.
kind of uses.
Okay. Okay. So have you so you made electrode. So you use
Yes.
composite or like what kind of material basically you search or you use?
Uh, so basically we prepare. I am like we prepare different carbon-based materials along with other modifications
Hmm.
for specified like devices,
Hmm.
and we test that electrochemical studies of it. I
Okay.
guess I have answered your question. I'm not sure.
Okay. So any so like for the composites, what's method usually you opt or you have been using?
Hydrothermal,
Okay.
uh, also with the sol gel,
Okay.
sonochemical.
Okay.
These few methods we use.
So what
CVD,
CVD also?
yes.
Okay. So what happened in the sonochemical?
Sonochemical technique, actually, uh, we are like I'm also new to it, but it is by dissolving in some solvent,
Hmm.
depending on the material,
Hmm.
and we ultrasonic it at different for different lengths of time,
Hmm.
and prepare the desired phase and shape, uh, size of that material.
Hmm.
I am not in de- in depth. I've not gone to it, but it is a new method of synthesis.
Okay. Okay. Fine. Okay. So we'll see again this property. So here your carbon fiber categories for industrial application. So let's say if you are going to the industrial, that requires some property for a different kind of application. Again, so here you will be having first thing is your strength. Let's say here they are saying a tensile strength and the tensile modulus. I hope it is clear. Do, are you aware about this strength and modulus and the yield? What is yield?
Yes,
Okay, na? Okay. So if not, then you can follow maybe the in the last lectures I have covered, or in the lectures you can see, or in any mechanical property of materials books you can follow. So carbon fibers are divided in two classes based on the overall mechanical performances. First thing is your high performance carbon fiber. Second is your general purpose carbon fiber. So basically, you can't say it is a low performance. That's why it is saying a general purpose. But what does that mean? It is a high performance, but it is not very comparable to the high performance carbon fiber. It has some low performance. Okay. Now here you can see this is your general purpose grade somewhere here. So this is the plot between a tensile strength and the tensile modulus. This is your high modulus type. So here you can say, because it's the fibers are aligned this horizontally. Here this is a high strength where your fibers are aligned vertically, right? This is your high strain, high strength type. Basically, it's a mixing of both kind of a texture. Here it is an intermediate modulus type. Okay, so this is your high performance grade. So if some material which comes this range, okay, where you will be having a good tensile modulus and a good tensile strength, that is your high performance carbon fiber. But if you will have a, in this general purpose, you will have a tensile strength and the tensile modulus both low. Here you can see a ultra high modulus type, the zigzag kind of a structure. So on the basis of, this is saying the percentage of the strain I think you're applied. This is a breaking strain. After that, your material will break after a certain amount of a strain when you will apply. So I hope that it is clear. No, we have seen the stress and the strain when you are applying. Sorry, here somewhere your material will fail. Okay, so this is your breaking point. After this stress, your material will break. So here also on the basis of your what property or the what mechanical property you want, it could be a high performance, it could be a general purpose, you can say, where you don't want a very high strength. Okay, so because to achieving a property itself that requires a lot of process, as a consequence your cost will enhance, the uses of your energy will enhance, so ultimately your economic will be in trouble. Suppose if your application don't want very high specific property like a very high strength and the modulus, you don't need to go for a very that kind of a orientation of your structure, or let's say you can say a processing technique. You can have some simple and then from there you can get some normal property material with the normal property. But let's say if you want certain a very high specific property, you will require that kind of a material, increase the cost. You will require a processing, again increase the cost as well as the requirement of your energy. You will require a lot of manufacturing unit, because that is not a one process. It is a combined of many small steps. So in this way, that's why it is saying the high performance, where you will require a, I mean, that kind of a material will be used only where you will require a high performance, that will give you a high performance. But you don't require that, then you can use a normal grade material, right? So in the carbon fiber also, they have categorized in two categories: high performance and the general. Okay, any doubt?
No.
No. Okay. Okay, just wait for few minutes, I'll be back. Okay. So now we have seen enough of the carbon composites. What are its, where can we use, or what is its what kind of a mechanical property it will give, and on the basis of it, where we can decide that where we want to use it or not. Now, this can be made. Okay. So after deciding everything, the main thing as a metallurgical engineer or as a material scientist, it comes like a preparation or the manufacturing. How will you know synthesize or the manufacture it? So this composite basically can be prepared by the heat treatment of carbon fiber and resin or carbon fiber and pitch. So heat treatment of carbon fiber and resin or carbon fiber or pitch. The pyrolysis, I hope that you are very well aware till now that what it's mean by the pyrolysis. We have seen enough of this pyrolysis process where in our previous lectures. Pyrolysis of hydrocarbon can also be used for forming the matrix. Carbon fiber are added to the matrix. So here you will have a matrix and you will add the carbon fiber, and what you will do, you will heat it at relatively low temperature. Now resulting material is impregnated with, now whatever the material you will come after this process, that will be impregnated with the resin. Okay. And pitch, you can add a resin or you can add a pitch, and then you will heat it to the higher temperature. In this, here you will require a low temperature, but here you will require a high temperature. Pores can also be filled by pyrolysis of hydrocarbons, very slow process. So here this is the schematic. So reinforced in carbon composite, we are using reinforced as a carbon fiber. Now this carbon fiber, thermosetting resin, thermosetting pitch, or you can use a hydrocarbon vapor. Thermosetting pitch, how you will be adding this? Solid phase pyrolysis. You have to use it high temperature around 1000 to 1500 degrees centigrade. After that, you will impregnate this, and after impregnation again at high temperature 1500 to 22 degree, you will heat it, and then you will get a carbon composite. If you are using a thermosetting pitch, then you have to go for the liquid phase pyrolysis. In this process, you will be using a temperature of normal temperature 550 to around 800. Again, you will do the impregnation and heat it to the higher temperature, and here you will require a again one more time heat treatment in order to get the composite. If you are using a hydrocarbon vapor, then a vapor phase pyrolysis will be required, and there you will be giving a temperature of 800 to 1200. Now after impregnation, you will require again heat treatment to the high temperature at around 22 to 2750 degrees centigrade in order to get the carbon composite. So this is the process flow, that how can you prepare a carbon composite. So it depends on here a carbon fiber resin or the carbon fiber pitch. Okay. And also you can use a hydrocarbon. So depending upon from where you are starting, whether it is a resin, pitch or the hydrocarbon vapor, you will require to follow this kind of a this flow, right? That what temperature you have to maintain, and after that impregnation, what temperature again you have to give the heat treatment. So these are the process in order to get the carbon composite preparation. Okay.
Yes, sir.
Okay. Now comes the properties, applications, and challenges. So wherever you will see a material, need of material, that should have some property, but with that property, that will come up with some challenges also, right? So that's why there are a keep on development of the material perspective in order to overcome the challenges. So let's say in case of this carbon-carbon composite, it has a lightweight density, okay, lightweight to density, low thermal expansion coefficient. What is thermal expansion coefficient?
The amount that the material expands like on heat treatment.
Okay. It's basically showing you the thermal property. Suppose if you're exposing your material to the high temperature, then how it is behaving. Okay. Now the thermal conductivity. Thermal conductivity, what is thermal conductivity?
How quickly the heat transfer can occur through the material.
Okay. And it is high thermal shock resistance. So what is this? Maybe I have discussed earlier, thermal shock resistance.
Uh, it resists sudden change in temperature.
Yes, so it can, also if you will apply some thermal shock resistance, does that mean when you will expose this material to the sudden temperature change, it is able to sustain that sudden temperature change. Okay, so that's why your material should be thermal shock resistance. You are applying from, suppose if you are heating your material, let's say 500 degrees centigrade, and suddenly you quench the material to the normal room temperature, or let's say in a ice water, then it could be able to resist the that shock, right? So that is your thermal shock resistance. Low resistance in high pressure ablation environment. Okay, when you will be using exposed to the high temperature, sorry, high pressure. Now, as I said in a very beginning of this class, I have said about the aircraft or something. So carbon composite is a very good as per the property that you can use this for the very specifically spacecraft application. This spacecraft, I basically it's my personal you can say a favorite, or the I like this spacecraft. I have this interest that what kind of a material is used in the spacecraft, because space is something which is very very challenging. All the rules which you are following, all the properties that cannot work in the space. Okay, so that's something which really excites me when I heard this spacecraft, because when I see some videos or something that some aircraft is going into the space, so everything is not gonna work as per the rule in the earth. Okay, so there you have to there you have a lot of challenge as per the material property, and I mean, what are the requirements you want in this space? So this material is very good when it is, using for the spacecraft kind of application. High performance braking system, engine components. Again, engine components you will require a good mechanical strength. There is a Just a sec. Yeah. So that also requires a keep on, in engine you will require a good strength so that it can sustain the weight or whatever the weight it is carrying. X-ray target, yes. Nowadays, I think in the X-ray targets are new materials which is using as a carbon composite. Heating element also you can use it as a heating element. And yeah, so what is the challenges here? The first thing is your property optimization. Okay, interface property between fiber and the matrix. So wherever this interface kind of a a thing, suppose if you will have fibers and the matrix, so there is a little bit challenge when something is coming for the interface. So very strong and fiber matrix bonding may lead to material failure, while a controlled adhesion at interface may improve the overall performance and the strength at high temperature. So when it will have a a very strong bonding, so there is a chances of a material breaking. Okay, so in order to get overcome of this kind of a challenges, it should have a controlled adhesion between this fiber and the matrix. It should not be very loosely, it should not be very strong bonded. The second thing is your oxidation. Oxidation, I mean, wherever in the carbon kind of a material will come, then you will have probably a problem related to the oxidation. So in this composite, it is tends to oxidize in highly oxidative environments at more than around 450 or 400. This can be solved by using antioxidant coating. You can use some kind of a coating, or you can use some inhibitors, let's say a boron, silicon, zirconium in the precursor. So there are some materials which you can add as an anti coating or antioxidant in order to resist the oxidation of your composite. So yeah, this is some kind of a challenges that you can face in order to whenever you will be seeing a manufacturing. So these are certain problems. In India, has a national program for developing this composite. Indigenous carbon composites have been used for making nose tip for the Agni missile. Oh, that is also a spacecraft, and brake pads for light combat aircrafts. Okay, so this carbon composite is using in Agni missile nose tip, making a nose tip. Okay, because it has a high strength. So when there is a nose in the spacecraft, the main part like a tip kind of a thing, so all the pressures will go and that will divide. So that's why you have seen in the aircraft or in the flight, the front part will be like this. It's not, you can't see like a this kind of a shape. Okay, so that will give you other, that will resist, so that's why it will cut down the pressure. Okay, also it can sustain the high temperature, and also a brake pads of a light combat aircraft, right? So in the brake pad also you will require a good mechanical strength. So in the combat aircraft also, the researchers or the scientists are using this kind of composites. So yeah, it's a good application, good material, and overall everything is good. So probably if you will have any chance to use this kind, work on this kind of a material, then it will be a good opportunity, right? So here we have seen this. Basically, now we are going through the carbon composite where you are not we using a polymer. We have seen enough of the polymer we have used. What kind of a manufacturing and what is the applications that we were using for the polymer. Okay, so now we will be seeing this carbon metal composite. So you can basically in the short form we call it CMC, carbon. This stands for the carbon, this is for the metal, this is for the composite. So have you seen anywhere where you have seen the carbon metal composite? Hello.
Yes.
So I'm asking, have you seen anywhere using this kind of a carbon metal composite?
No, carbon concrete. I've heard they are trying to build uh, RCC slabs with carbon now.
Okay. So not about the carbon metal composite.
No.
Okay. Just like that. My phone is ringing. Okay, let me silence this. Yeah. So, uh, okay, let's see where firstly we'll be seeing the metal matrix composite MMC. So composite material where the additive is any mechanically harder phase such as your fiber, tubes, whiskers, particles, etc. and a matrix composed of a metal alloy or intermetallic component. Okay, so here again you will have the matrix and additives, or you can say a reinforcement. So in the MMC, basically a metal, because it is MMC. Alloy is also there is a one component at least should be a metal, or you can say intermetallic compound. There will also be a your metallic kind of a. I mean the metal will present, so you can use alloy or the intermetallic compound or the metal. But as a additives, you can use like fibers. You can use tubes. We can use whiskers. You can use any particles. Let's say a nanoparticle, microparticle, anything. So in carbon metal composites are mainly based on the carbon fibers. Okay, so here in MMC you are using matrix as a metal, additives also in the form of this. But in the CMC when you will use, so here matrix. Okay, so here your carbon in this composite, this metal will be the matrix, and your additives will be your in the form of carbon fiber. So this will be your mainly additives, right? Now, if you have gone through the this mechanical diagram of this, let's say here, So this is like brittle for the brittle material, but metal is ductile. Okay, so you will have this kind of a behavior. So this is your ductile nature. This is your brittle nature. So material for the metal follows this behavior. Okay, it won't break to the very sudden. So the metals are ductile and malleable. One can make a thin sheet of a metal. Okay, hence for certain applications such material can be useful. Addition. Okay, so where suppose if you will have a ductile nature, it is a malleable, you can make a sheet, you can get into any shape, you can have a lots of applications where you can use metals. But if you add your carbon fiber into this good property of a metal, okay, now suppose you this metal will have a high temperature metal, if it can resistance the high temperature. Now if you will add a carbon fiber, then it will give you a high strength as well as the at high temperature. Okay, so this is the perk of adding carbon fiber into the metal. In order in the high temperature you can achieve a good strength. So in the application where you want to use a your material at very high temperature, but you also need a certain specific good strength, then you can use a CMC, which is carbon metal composite. Okay, so now how you can prepare this composite, or the what are the applications mainly where you are seeing using this CMC. So here two things is there, carbon and metal. So you should know that what can you achieve by this by using an individual's property. So in the metal, it has a good thermal conductivity. Also, it will have a high thermal expansion coefficient. But carbon structure will have a low thermal expansion coefficient. Now, a thermal, sorry, when you add this together in CMC, here you will have a metal which is also conductive, carbon which is also conductive. So this both will give you a better electrical conductivity property to your composite. Now because there is a thermal expansion coefficient here in the metal, it is high, but here it is low. So that can give you a small thermal stress during the operation because of this mismatch. So the property of the metal, and for good manufacturability, low carbon fiber content is used. Okay, so here also when you are adding this, then it is also important in your metal matrix how much carbon fiber you are adding, whether it is a 10%, 20%, or you are using a 90%, or you are using 80%. Okay, because it is an additive. Okay, so low carbon fiber content is used in order to get uh, I mean to efficiently you can use the property of this both material. So commonly used metals, okay, so since it is a metal composites, so what kind of a metal you can use? So there are a bunch of metals in our periodic tables, but here you can see aluminum. It has some good specific property. Magnesium, it is also a light metal. Nickel is also one of the most commonly used material. Copper, anyone has seen, copper is also having its own property. Titanium is also a light metal. It also has some its own property. So every material, has their own property. So in order to use those particular material for certain kind of application is selected by the property of that specific metal, okay, or the property or the desired property you want. Now there is a processing, or you can say a preparation method, how you will prepare this kind of a composite. So there is a powder metallurgy. So powder metallurgy, here it is saying it is a not a very small thing saying a powder metallurgy, but it has a lot of concepts when you will actually go through the powder metallurgy. So there is a lot of powder metallurgy book if you want to expose your knowledge, explore your knowledge in the field of powder metallurgy. You can have some a good reading or good study material. So ball milling. Okay. So do you know ball milling? Anybody knows ball milling? Okay, so ball milling is a process where milling it means there is a mixing of, sorry, but here you will be using a balls. So a lot of balls will come in contact with your material, and that will grind your material, milling, okay, so that you can get a certain desired size of your, let's say, whatever the material you will have. So here what you will do, here you will add your carbon fiber and the metal, and you will do the ball milling. After this ball milling you will do the die casting. Okay, this is also one kind of a casting process. If you don't know, you can read any kind of a casting book. There you can probably understand all kind of a casting, like die casting, or the or different kind of a casting process, or the molding also. Now yes, after that you will do the heat sintering. In the sintering, what you will do, the sintering process, that will make a compaction and the unwanted particle will can remove, and then you can do the extrusion. Whatever the shape of the required shape you can want, you can use it by the extrusion process. Now there is a diffusion bonding. In this, there will be the layer of carbon fiber performs, and the metal sheet will be there, and there will be the compression. Okay, so that it can make a bonding by diffusion process, so that low temperature compression. After that, you can use a liquid state processing. So here casting mix additive in a molten metal and perform casting. Suppose, let's say if you will you want to make aluminium and carbon fiber composite, you will take aluminium and you will melt it. So here you will have a liquid, you will add some carbon fiber or let's say whatever you want, and then you can directly cast it whatever the shape you want here in your mold. Okay, so this is a very simple process. Liquid infiltration is the another kind of a manufacturing process from which you can manufacture the CMC. So here molten metal is poured on the performs at high pressure, and then you will do the solidification. Deposition process, ion plating. In this you will use a metal evaporation techniques on carbon fiber under argon plasma. You have to maintain the plasma, and then you will do the hot press auto infiltration. Plasma spraying is also a deposition technique where you will be using the matrix will be sprayed with plasma, and then followed by the hot press auto infiltration. Now you can see the applications where we can use is this in the heat sink, in the electronic application, for the advanced tools, for the manufacturing of bearings, and the application associated with improved electrical conductivity, because it wherever you want a good electrical property as well as the mechanical property, there you can use this CMC. So here you can use a carbon see the carbon fiber fabric between metal sheets for diffusion bonding. So okay, so this is your carbon fiber fabric, and this is your metal sheets. Okay, so now here you will be using a diffusion bonding, and this will diffuse, this layer will followed by the low temperature compression, so that your carbon fiber and the matrix will diffuse. Okay, so I hope it is clear. If not, you can ask any question if you will have any, if you have any doubt. Now, after metal composite, there is another kind of a carbon non-polymer matrix is carbon concrete composite. So again, how will you prepare and where are the applications that you can use? So here the carbon additives. So here your matrix will be your concrete and your additives will be your carbon. Okay. So now why you are using this or what will you get by making this kind of a composite. So the thing is here you will get a high mechanical strength, or let's say you can say structural strength. A structure weight reduction, here you will get a high weight I mean the lead weight lead I mean the less weight reduction. You will get a waterproofing, noise will also reduce, and the fracture detection by changing electrical resistance of the fiber. You will get electromagnetic shielding also. Okay, so the carbon fibers here are used in various ways to improve structural properties. Wherever you want to improve the structural properties of carbon concrete matrix, you can use a carbon fiber. Then the carbon volume fraction is much lower compared to the other carbon composites. So it is very low. You can take between let's say a 0.5 to 1% volume. Now, chop GP grade carbon fibers will be mixed here. Your carbon fiber will be mixed into the concrete non-woven carbon fiber made for shielding. Now this carbon fiber reinforced polymer sheets for providing external support sandwich layer. Okay, here you will be having. Then the carbon fiber can be wound around a pillar for improving the strength. Now stands of this CFRPs for strengthening cable-like structure also. This can be added to concrete for pore filling. Okay, so carbon nano material, where you can use a nano scale carbon material so that the pore can also fill and it will give you a good property. Often these GB grade fibers are used with concrete. Okay, so here there are some diagrams where you can see the winding carbon fiber on a concrete pillar. So this is your concrete pillar. Okay, and here you are winding a carbon fiber. Here carbon fiber is coated structures. This is your carbon fiber is coated. Here external structure supported using CFRP. This is your bridges with carbon fiber tubes. So this can be also used. This is like a bridges. So what are the this has a good property, good mechanical and the structural elements. Plus along with the advantages, there will be it comes with the some challenges and the problems. So development of slip surface where fibers have a poor adhesions, here it is the main challenge, and the overall failure of structure and the reuse of carbon fiber is also it can failure of a structure. It can fail at certain time or at certain way. Is it clear? If you will have any doubt or questions, you can ask. Now, the very interesting material came here, which is nothing but the graphene. And graphene is nowadays everywhere because of its very specific and exotic property. It has been using in all over the world for the different kind of application. So now, it is a defect-free single atom thick layer of graphite is known as graphene. Okay, so in our previous lectures, you must have seen, uh, you must have seen that the graphite is a layer. Okay, but if you will break this layer and you will only get a single layer. Okay, so this is your graphite, but after breaking you will get a single atomic layer thick, which is a graphene. So graphene was traditionally produced as a precursor for graphite manufacturing using pyrolysis. Okay, so here you are using in as a suffix is used with graph of graphite. Okay, so similar to polycyclic hydrocarbon, example anthracene, naphthalene, as per the IUPAC recommendation. So each carbon atoms make, so here in the graphene, each carbon atoms will make 3 sigma bond, 1 pi bond. And these pi bonds are delocalized. And we call it pi band. So sigma bonds are responsible. So here, because here 3 sigma bonds, it is responsible for the mechanical property of the graphene. But the very interesting is that graphene is a conductive material. And why? Because of this pi bond. So this is also electrically conductive material. Now the sigma bonds are very strong with the in plane bond length smaller than that of the diamond. Hence, graphene is considered stronger than the diamond. Why? Because the sigma bonds are very strong with the in plane bond length smaller than that of the diamond. Here, the sigma bonds results from a strong wave function overlap between a carbon atoms and its nearest neighbor. It has a high optical transparency of a single layer. So here you can see the TEM image of graphene sheets in bulk carbons. Okay, this is a TEM image how the atoms are in single layer. Here you can see the all the atoms. You can see this kind of you know some hexagon kind of a shape. You can probably see. So in principle, the term graphene should only be used for a single defect-free layer of graphite. Okay. So here it is not something related. I mean, it is graphite is a multiple layer, but when you will break the single layer, or you can say a one atomic thick layer, is nothing but the graphene. Now what is the crystal structure of this graphene? So here you can see, you know this is your carbon. So two neighboring carbon atoms, CC bond length. Okay, so two neighboring carbon atom, let's say here and here, it is 1.42. Here you can see a 1.42 is the bond length, are not equivalent. Atom A cannot replace atom B by only one translation operation. Thus, a single atom or the entire hexagon cannot form a Brevis lattice. Gray rhombus, here you can see this gray rhombus, represent the primitive unit cell. Important crystallist parameters are here. Lattice vectors. Here you can say A1, A2, sublattice vectors. Here B1, B2, B3, translation vectors T1, T2, T3, and the first Brillouin zone. Now, what is the property of this graphene? Because of its property only, the graphene is worldwide known. So it has a certain kind of a specific property that because of that certain property, it is been using worldwidely. So the electrical conductivity of graphene. So I have explained because of the pi bond. Okay, one single delocalized pi bond. It is conductive. Now the conductive along zigzag direction. Okay, so here you can see a conductive along the zigzag direction. Semiconductor along armchair. There is a band gap. Okay, so semiconductor armchair. So here the voltage is applying armchair. This is multiple zigzag paths are always possible. Here the graphene folded into a tube shows the conductor and semiconductor behavior along depending upon the zigzag or the armchair geometry. So here you can see this is a semiconductor armchair because it is having this. Here it is a conductor because it is having this zigzag. Semiconductor because it is a chiral. Okay. So Chiral tubes are semiconductor. CNT will be covered later in this course. This CC carbon-carbon bond length in graphene is 1.42 and in a diamond it is 1.5. Hence, single graphene layer is considered stronger than the diamond because the CC bond length is smaller as compared to the carbon. Okay, so the electron in graphene do not behave in the same way as in bulk carbon due to quantum confinement, change in material's electronic property when the sample thickness is less than 10 nanometer. Carbon atom diameter is 0.14 nanometer. Now, when you will be going to the history of the graphene, it is a single layer graphite has been known and studied for at least 70 to 75 years based on the available literature. First report of the band structure of single layer graphite was published here in this 1947, and band structure of 2D graphite was used for understanding the 3D graphite, and term graphene was first used by Hence, Peter Boehm et al., who prepared graphene experimentally in 1962, define of graphene was added to IUPAC database in 1994. Epitaxial few layer graphene growth started in 1970s, and then the few layer graphene was studied using graphite intercalation of compound in 1965. Then the address James and the Konstantin Novoselov removed a graphene layer from graphite using an adhesive tape and characterized it. They were awarded the Nobel Prize for this work. Okay, and in parallel, hydrocarbon pyrolysis was optimized for fuel layer graphene and other carbon nanomaterial production. So I hope this is a good history that you can also read in the Wikipedia or somewhere. But uh, Yeah, so let's discuss some questions for the today's class. So the question at the last I'm taking, graphene naturally contains some waviness even when it is defect free because bond length in graphene is not well defined. 2D material are unstable. Carbon atoms in graphene are always vibrating. There are always some non-six membered rings. So I think as we have seen the graphene material slide. So because of the carbon atoms in graphene are always vibrating. The term multi-layer graphene is best suited for which of the following material? Two or more layer of randomly rotated graphene sheets, two or more layer of graphene in ABAB arrangement, one atom thick layer and single and defect-free graphite. So it is two or more layer of randomly rotated graphene sheets. A suitable method for shaping a composite made of short carbon fiber is metal matrix composite diffusion bonding casting. Acha, suitable method it is asking. So shaping a composite made of short carbon fiber. So definitely it is a casting. Okay, where you can use a short carbon fiber. Turbostatic carbons can be used for more than 10 layer of graphene sheets with some curvature. Select the correct sequence of process that takes place during CVD of graphene. So here the first thing is your pyrolysis, then the transport of carbon species, then the surface migration, then the film growth. So this we will be seeing in the next lecture. Graphene is considered a stronger material than diamond because of its has a lower CC bond length in the graphene it is 1.42, in the diamond it is 1.54, so it is lower than the graphene, so that's why it is stronger. Which of the following is true about graphene? That the CC bond length in graphene is greater? No, it is not true. Graphene is only theoretical semiconducting. No. A defect-free single layer, it is true. Apart from chemical vapor, it can also be produced by epitaxial. Yeah, so the third and fourth is true. So these are some questions, and next week we'll be trying to cover some more questions. And that's all for the today. Hope you guys enjoyed today's lecture, and see you in the next class.